Hello students! In this video, we start looking at what we call infinite series. So this is an introduction to infinite series part 1. We just finished looking at infinite sequences. That is a stepping stone for our next topic, which is infinite series. Now students often confuse sequences and series, and so I'm going to start by looking at a comparison between the two. On the left, we have an example of an infinite sequence. A sub n equals 1 over n. And let's just recall that in an infinite sequence, the n's represent positive integers. That is, the sequence is really a function defined on the set with a domain of positive integers. This particular sequence 1 over n is the sequence 1, 1/2, 1/3, 1/4, etc. It's an ordered list of numbers. Again, this infinite sequence should look familiar to you. Now, compared to the infinite series, we have the same pattern 1 over n, but this time we pair it with this symbol in front of it. We call that symbol the sigma notation symbol. And if you recall from Calculus 1, we did see a sigma notation before. We saw that with a Riemann sum. I don't know if you remember or not. Sigma means sum, and this particular sum starts at 1 and goes to infinity. So if we were to take the sum from n equals 1 to infinity of 1 over n, we would get the sum 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. The big difference between a sequence and a series is that a sequence is a list of numbers, whereas a series is an infinite summation. Now, remember, sequences and series are very different, and so the way that we tell if a sequence converges is different than how we tell if a series converges. In fact, deciding if a sequence converges is much easier than deciding if a series converges. So let's take a look at this example. The same sequence we were talking about before, a sub n equals 1 over n, where n goes from 1 to infinity. If you recall, how do we find whether a sequence converges or diverges? Well, we take a limit as n goes to infinity. So if we were to take the limit as n goes to infinity of 1 over n, that's just the finite number 0. Because our limit is a finite limit, we say that the sequence converges, and it converges to the limit of 0. Now let's take a look at the corresponding series, the infinite sum of 1 over n from n equals 1 to infinity. That's the sum 1 plus 1/2 plus 1/3 plus 1/4. This is a sum, not a list, it's a sum. That's 1 1/2 and add to it 1/3 and then add to it 1/4 and then add to it 1/5. Now, even though these terms are decreasing, do these terms add up if I kept adding forever and ever and ever? Do they add up to give me a limit? Do they add up to be a specific number? Well, if they did, then we would say the series converges. But I'm going to tell you that this special sequence, this special series is called the harmonic series. And harmonic series always diverge. So this harmonic series diverges, and we'll take a look at why later on, but the harmonic series diverges. Even though the terms are getting smaller, they don't get smaller fast enough. And that concept of not getting smaller fast enough and convergence and divergence should ring a bell. We talked about improper integrals where our integrals either converged or diverged, and we said it had to do with how quickly the graph approached the x-axis. Are you getting close enough, fast enough? And that's the same idea with convergence for a series. So that's a quick introduction to tell you the difference between a sequence and a series, and kind of looking at the convergence of what a sequence is versus a series.